All right, so this is the first of the videos on one-way ANOVA, which comprises chapter 12 in our textbook. I believe there'll be 2 videos total, okay? So first off, ANOVA stands for Analysis of Variance. So we're gonna measure variability between a couple of different things. The basic idea here is we're gonna use one-way ANOVA when we wish to compare the means between more than 2 populations or groups. To see whether any of the means differ from the others. Now, if we just have 2 populations, we've had in this class a lot of different tests to see whether those population means are the same or different, okay? We had difference of means, we had ratio of means. We've done a lot if you look back with just 2 populations, okay? So in these setups that we use one-way ANOVA, our null hypothesis is going to be, well, first off, we're going to have G different populations or groups, and the null hypothesis is that each group has the same mean, and the alternate hypothesis is that at least 2 of the means don't equal each other, okay? Now, the thing we need to look at and kind of measure is how variability of 2 types are interacting. So in this first data set, I've got 3 groups, group 1, group 2, and group 3, and I've got a box plot for each of them. And if you recall, this central line was the median or the mean or something like that, these populations. And it looks like those means differ, right? And it looks like they're steadily getting larger. But there's a bit of a problem here with this data. Within each group, there's an awful lot of variability from the group mean. And so the question becomes, how much of this difference in means is due to the variability within each group? And how much of this difference of means is like truly there? Because remember, we're going to have 3 separate populations, and then I'm going to sample from each population and create this box plot. So it could just be that the sampling and the variability, the large amount of variability within each population is creating this artificial difference of means. Or data set 2 here, same setup, 3 populations, grab a sample from each, make the box plot, means look different, and the variability within each group seems relatively small. So we might be more inclined to believe that this difference in means that the box plots are showing is actually there, versus over here where the difference of means could just be caused by how much variation there is in each population. Okay? All right, so what we're going to work on is how do we figure out how to compare the variability from the mean within each population to the variability between the means of the different populations, okay? And what we're going to do is we're going to reject the null hypothesis that all these means are the same if the variability between the groups is much larger than the variability within the groups. So that's going to be the key idea that we're going to come to in probably about 20 minutes, okay? So if we have a lot of variability between the different groups, when compared to the variability within the groups, then we're going to conclude that, you know what, the means probably aren't the same. There's probably some differences there. Okay, now, though we won't cover it in the textbook, I thought it'd be useful, like one-way ANOVA begs the question, well, is there other ANOVA? And yes, there's also two-way ANOVA. So this will be the only thing on two-way ANOVA. We're not going to do any problems on it. It's not covered in the textbook, nor will it be covered on our exam. All right, so two-way ANOVA. What we're going to do is we're going to look at the setup here is going to be, we're going to have one quantitative response variable, so like numeric 12, 18. The response variable, the output is going to be numeric. The inputs, the predictor variables are going to be categorical, okay? So for example, the response variable could be the amount of dirt that's being removed from clothes in one wash cycle. And the 2 categorical predictor variables are which detergent we use, and perhaps it's Tide or Kirkland, or maybe there's 6 different brands of detergent, so those are categorical. And then the water temperature used, which I guess cold, warm, hot might be 3, but maybe there's more categories for that variable as well. And what we use two-way ANOVA to determine is a couple of different questions. can we get a clear winner within each of the predictor variables? So is there one of these detergents that removes more dirt than the other? Is there one of these temperatures that removes more dirt than the other? So that's the first two. And then it can also help us address the question, is there a combination of these two predictor variables that is optimal for dirt removal? Okay. All right, so that's all we're going to talk about on two-way ANOVA. So, all right, so now, unfortunately, we're going to get into a bit of an alphabet soup because we'd like to go back and figure out how do we determine this notion of when the variability between the groups is much larger than the variability between groups. Sorry, vice versa. How do we figure out when the variability between groups is much larger than the variability within groups? All right, so gonna have to figure out some notation and, well, and some probability distributions, okay? All right, so first off, we're gonna have capital G groups, each with mean mu sub 1, mu sub 2, etc. From group I, so like group corresponds or is synonymous with population. So if you hear group, you can think population. So we're going to take a sample size n sub I from the ith group of population. So we got a population, we sample from it, and that's what we're going to study, that sample. The total number that we've sampled will be the sum of those n sub i's over all the groups, and we'll call that little m. All right. So from each group I, we've got x sub I, n sub I, a random sample size n sub I, and we're going to make an assumption, all right? So this is an assumption of the model. We're going to assume that that random sample follows a normal distribution with mean mu sub I in the population and a variance sigma squared. So this sigma squared is another assumption. We're going to assume that's the variance across all the populations. So we're going to assume a constant variance, okay? So within each population, our samples are going to be normally distributed, and all those normal distributions share the same variance sigma squared, okay? All right, so now we're going to calculate some means. So first off, x bar I dot, this is going to be the mean of the sample from the ith population. So we're going to take all the data from that ith population from 1 to n sub I, add them together, and divide by n sub I. So that's the mean of the sample from the ith population. X bar I dot. Sample mean population I. And then we want the overall mean as well. So that's going to be x bar dot dot. And there's a couple of different ways you could calculate this. We could add up all the data within one sample, and then add all the samples, that value for all the samples, and then divide by the total number n, okay? So that's just adding all the data up, dividing by n. Or I could grab the sample means, multiply each sample mean by the size of its sample, and add those all together and divide by n, okay? So these two things are equivalent. And x bar dot dot, that is the overall mean, okay? All right, so now there's some space here. Couple of panels of the alphabet soup. So first off, we'll start to measure the variability between these differing groups, these G different groups. So SSTR is going to be the treatment sum of squares. So when you see the word treatment, you can think groups or populations, okay? So SSTR, what I'm going to look at is the difference between the sample mean from each group and the overall mean. So look at that difference, square it to keep it always positive, and then sort of scale it up by how many people are in that sample, right? So we're going to measure this distance multiplied by the number of elements, data points in that sample from the population I, and then add that up over all the groups. So that's sort of the total, one for each element in the data set, difference of means, okay? What the square difference of means. So that's SSTR. And what it's measuring is how much these sample means are differing from the overall means, okay? Scaled by the number of data points, okay? we want to scale this down a little bit so we can compare against different populations. We don't want this number to be large just because we've got a whole lot of data, all right, a lot of data points. So we're going to scale it down. We're going to take that SSTR and we're going to divide by the number of groups minus 1, okay? So this will sort of tell us the average sample mean distance apart from, I'm not saying that well. We're just going to scale it down by the number of groups we have to sort of provide some uniformity. And we'll also see it has a probability purpose later on, okay? So this is called MSTR, or the mean squares for the treatment. All right, so again, this is measuring the variability between the samples, between these populations, right? Now we got to measure the variability within a group as well, because we want to compare those two variability measures. Let's see. This is where it gets tricky. All right. So now we're trying to measure the variability within a group, okay? So SSE is going to be the error sum squares. And if you recall from earlier, error was also synonymous with residuals, difference from the means, difference from the sample means. So for the error sum of squares, what I'm going to do is I'm going to take my individual data points and look at the distance between the individual data points and their sample means, square it, add up over all the data we have in that sample, and then sum over all the different groups or populations we've sampled from. So this is the total difference from means from each data point and its local mean, right? We're going to scale it down. So we're going to take the mean squared error residuals, and that's going to be that error sum of squares divided by n minus g, the total number of data points minus the total number of groups. And we'll see that this has a good probabilistic or probability purpose later on. Okay. All right. So we've measured variability between the groups. We've measured the variability within a group, within the groups. And now we can also talk about the total variability. So SST, and this is the last of the letterings. SST is the total sum of squares. And here, this is much like SSE, but now we're going to take each data point and subtract or figure out its distance to the overall mean, x bar dot dot, square it, add it up over each element of the sample, and then over all the different samples we've taken, okay? So this is measuring the distance from the overall mean of all the samples, okay? And we can show algebraically that the total sum of squares is equal to the error sum of squares plus the treatment sum of squares, which heuristically should make sense. The total variability in the data is either from the variability between the groups plus the variability within the groups, okay? So heuristically, that should make sense. And we could actually grind through this expression algebraically, okay, which we probably will do. And that's all the variability there can be. Either it's between the groups or it's within the groups, okay? So that's all the variability we've got. All right, now I'm going to wheel us over to the last 3 panels to finish off this video. Okay, lighting's not as good over here. Hopefully it still works. Okay. All right, so we've got the alphabet soup defined, and now we're going to bring in the probability part to figure out how to actually measure and interpret our measurements, okay? All right, so that's where we ended on the last panel. The total sum of squares is equal to the error sum of squares plus the treatment sum of squares. I could divide each by the common populations variance, sigma squared. And what theorem 12.1.3 in the textbook takes quite a while to prove is that the error sum of squares over sigma squared and the treatment sum of squares over sigma squared are both independent. And if the null hypothesis happens to be true, then the total sum of squares over sigma squared is chi-squared distributed with n-1 degrees of freedom. And the error sum of squares divided by sigma squared is also chi-squared distributed with n-G degrees of freedom. Okay. Now, it also turns out, much like Poisson random variables, that if I add or subtract independent chi-squared random variables, the result is still chi-squared, right? With different degree of freedom, okay? So that's just like in Poisson. If you had two independent Poisson processes, one measuring the number of people entering a store in an hour, the other measuring the number of, I don't know, times a bathroom toilet gets flushed in an hour. If you add these two independent processes together and say, I'm interested in either somebody entering the store or the toilet flushing, that also is a Poisson process. And we actually added means in that case, okay? Well, in this case, the difference of two chi-square distributions, which algebraically speaking, if I take SST over sigma squared minus SSE over sigma squared, I have solved for SSTR. So SSTR over sigma squared is also chi-squared distribution, okay, with G-1 degrees of freedom. So that was under the null hypothesis. Now, the way you prove a difference or sum of chi-square distributions is chi-squared, independent chi-square distributions is chi-squared, is by looking at the moment generating functions of the two distributions, okay? All right, so that take-home message. Under the null hypothesis, the treatment sum of squares divided by sigma squared is chi-squared distributed with G-1 degrees of freedom. Okay. All right. So that's where we start with up here. This would imply the expected value of that SSTR over sigma squared is equal to G-1 degrees of freedom. That's how you calculate the mean of a chi-square distribution. And since sigma squared is a number and G-1 is a number, and this is an expected value, I could multiply both sides by sigma squared and divide both sides by G-1 and bring that G-1 inside. So I have the expected value of SSTR over G-1 is sigma squared, okay? Another way of saying that is the expected value of the mean sum of treatment squares is equal to sigma squared. So the G-1 is there because of the chi-square distribution. And this means that under the null hypothesis, so if the null hypothesis is true, the treatment sum of squares divided by G-1 is an unbiased estimator of sigma squared. Great, let's vaguely keep that in mind. Now, if H0 does not hold, this quantity tends to overestimate sigma squared. Okay, it tends to be too large. Let's also keep that in mind. Okay. All right. Now, independent of whether H0, the null hypothesis, is true or false, we always have that SSE over sigma squared is chi-squared distributed with n-G degrees of freedom. So this is always true. This was only true under H0, but this is always true. So I can get the expected value of the error sum of squares over sigma squared to be n-G. I can flip my two numbers again, and I see I have another unbiased estimator of sigma squared, namely SSE over n-G, which on a previous panel we defined to be the mean error square. Actually, what was that name? Mean squared error. Okay, so I have under H0, if the null hypothesis is true, I have two unbiased estimators of sigma squared. But if H0 is not true, I have one unbiased estimator and one estimator that tends to overestimate. Okay. All right. And that's going to be the key to how we measure whether H0 is true or false. Right. So final panel. So a little recap there. If the null hypothesis is correct, I have SSTR over sigma squared is chi-squared G-1. SSE over sigma squared is chi-squared n-G, and that was true whether or not H0 is correct. And SSTR is independent of SSE, okay? Now, this means I can take the quotient of two chi-square distributed quantities. So I take SSTR divided by G minus 1 over SSE divided by N minus G. So that's chi-square over another chi-square. It turns out when you take one independent chi-square divided by another independent chi-square, you create a new distribution called an F distribution, okay? And that's an F distribution with G minus 1 and N minus G degrees of freedom. So there are two measures of degrees of freedom for F distribution because it's coming from a quotient of chi-square distributions, each of which could have different degree of freedom. Okay? So this quantity is going to be our test statistic. We'll call it the F ratio. So when we have data and we want to see if the means of these different groups are the same, this is what we wish to calculate. All right. If we can calculate it, we know under the null hypothesis how it ought to be distributed. And if it varies from this distribution by too much, well, then we reject the null hypothesis. Something has gone wrong. Okay. All right. So if this F ratio, our test statistic, if it's a lot larger than 1, then we want to reject H naught. So the way we calculate our p-value is I take my F ratio and I look at the F distribution where under H naught it comes from. We look at the probability that the distribution exceeds that F ratio. Okay, so we're looking at the right tail of the F distribution for our p-value. Because much larger means that this numerator has overestimated sigma squared, while the denominator is the unbiased estimator sigma squared. So it's probably going to be bang on sigma squared. So either this thing will be about 1, in which case we'll accept the null hypothesis, or it's going to be larger than 1, in which case we start to think about rejecting the null hypothesis. Okay. All right. Now, in R, the way we calculate this probability or p-value is we're going to input the F, type in the F ratio there, display the 2 degrees of freedom for the F distribution, and we want the CDF of the F distribution. That would give me the left side. So 1 minus that would give me the right side. Okay. All right. Second video is going to be some examples on how to interpret the tables that R provides for us in this process.